Section 6.2 is entitled Dilations. If you think back to when we did all of the types of transformations, we did reflections, translations, and rotations. All of those resulted in a congruent polygon. But dilations does not. A dilation results in a similar polygon. So let's first define what a dilation is. A dilation is a transformation that preserves angle measures, which means that the angle measures do not change. So again, a dilation is a transformation that preserves angle measures and results in an image with lengths proportional to the pre-image lengths. So there's some words in here that are new to you. We have image and pre-image. The image is the new figure. The pre-image is the old figure. So just to reiterate, again, a dilation is a transformation. So again, we've seen other transformations like reflections, translations, and rotations, but now we have a fourth transformation called the dilation that preserves, so it doesn't change, angle measures and results in an image, so the new picture, with lengths proportional to the pre-image. So that's the old figure, so it's proportional to the pre-image lengths. The ratio of the lengths of the corresponding sides of the image and the pre-image is called the scale factor, just like it was called in the last section. And you always want to make your scale factor so that it goes from new to old. That's something that you definitely need to write down in your notes. New to old. You put the new picture, so the image, over the old image, so the pre-image. Dilations can also be called similarity transformations. So again, a dilation is just a transformation that preserves angle measures, but the lengths of all the sides are proportional to the original or the pre-image. And we find that scale factor by doing the new over the old as a proportion. So the image over the pre-image. So dilations and similarity. If a dilation can be used to move one figure onto another, the two figures are similar. So remember, similar means angle measures are the same, but sides are proportional, just like it was stating up here when we were defining what a dilation is. So let's look at the first example. It says triangle ABC is similar to triangle AFG. Describe the dilation that moves triangle ABC onto triangle AFG. It says moves ABC onto AFG. So this is the old and this is the new. So when we're asked to describe the dilation that moves triangle ABC onto triangle AFG, we're basically just asked to find the scale factor, which, remember from the last slide, means we're going to do new over old. So the new would be this entire length over here, not just the 10, not just the 40, but together we have 50. The original was from triangle ABC, and that was 40. So just to put that into lowest terms, we'd get a scale factor of 5/4. So I would say a dilation of scale factor (5/4). And a reader would know that that meant new over old, meaning we went from smaller to bigger. You can also combine dilations with rigid motions. So remember, rigid motions are translations, which means the shifting, reflections where you flip it over a certain line, and rotations where you rotate it about a certain number of degrees and in a certain direction. And remember, rigid motions do not change the size or the shape of the original figure, which is different than dilations because remember, the shape isn't changing, but the size is. So again, we're going to combine dilations with rigid motions. If a dilation followed by any combination of rigid motions can be used to move one figure onto the other, the two figures are similar. So if you look at the diagram here, it says triangle ABC is similar to triangle DEF. So they have shrunk triangle ABC to make it into triangle DEF. And triangle DEF is congruent to triangle GHJ because it was reflected over this vertical line. So therefore, since we had a rigid motion that moved the green onto the red, and the green was originally similar to the blue, that means now the blue is still similar to the red. So basically you would know that triangle ABC is similar to triangle GHJ. So let's see an example of combining dilations with rigid motion. So here's example number 2. Triangle ABC is similar to triangle FGE. So here's ABC, and we're told that it is similar to triangle FGE. Describe a combination of transformations that moves triangle ABC onto triangle FGE. So notice triangle ABC is smaller than triangle FGE. So we're going to need to have a dilation to make it bigger, and then we'll go from that new image and reflect it over the vertical line to make it into triangle FGE. So again, we're going to first start with a dilation, which means we need to come up with the scale factor. So again, remember we go new over old. So the new would be the big triangle ADE. So that side length that we're given here is not just 20 and it's not just 30, but it is 50 over the old, which would be the 30. So to put that into lowest terms, we'd have a scale factor of 5/3. So again, dilation of scale factor 5/3. So now we have it as a bigger form of itself, and now we need to reflect it over the vertical line onto triangle FGE. So our second transformation would be a reflection over the vertical line, and that would take us from triangle ABC onto triangle FGE. And now let's look at our last example, number 3. Use transformations to explain why pentagons EFGHD and RSTUV are not similar. So just upon glancing at this, it looks like they're similar. It looks like that this smaller pentagon just needs to be enlarged by a certain scale factor, and then we reflect it over here onto the bigger. And even when you break down the scale factors, you have 14 and 28. So from new to old, it would be 28 over 14, which is a scale factor of 2. If you do the next one, which would be 32 and 16, 32 over 16 is still 2. If you do 30 to 15, that's still 2. 28 to 14, again 2, and 20 to 10 is still 2. So we have a scale factor of 2. So it looks like we have a similarity transformation so that we had the dilation to make this get bigger by a scale factor of 2, and then we just reflect it over. However, if you put this one, after you blow it up by a degree of 2, and then reflect it over this way, this is what it ends up looking like. So you can see here, after you blow it up by a scale factor of 2, and then if you reflect that dotted over onto the right side of the picture, you can see that not everything lines up. The angle measures are not the same. So again, it looks like they're similar by a scale factor of 2, and then just you have to reflect it, but then the angle measures aren't the same. And you can especially see it in this angle right here. This angle measure looks significantly bigger than this angle measure right here. That's the one that, just from looking at it, looks the most different. I would say also possibly angle F here and angle S. You can see that this one is slightly smaller than this one. But again, especially once you blow it up by a scale factor 2 and then reflect it, you can definitely see that everything does not line up. So there is not a transformation here that makes these two pentagons similar. And that's it for this section. Make sure you write down anything you don't understand that we can cover in class before we move on, and we'll see you then.